In this video, we provide an introduction to isomerism. Isomerism is important in many branches of chemistry, including organic chemistry and inorganic chemistry. Here, our focus is going to be on transition metal chemistry, so many of the examples that we're going to be using to illustrate isomerism will involve transition metal complexes. Alright, there's many types of isomerism, many classes of isomers, and we're not going to see all of them in this video, but we're going to see a few of them that are particularly important to transition metal chemistry. Alright, first let's start with the definition of what isomers are. Two molecules are isomers if they have exactly the same number and type of atoms, but different properties. Alright, and the first two types of classes that we're going to see are going to be structural and stereoisomers. Alright, so let's write that down here. You have structural and then stereoisomers. And the difference is fairly simple. Structural isomers are those that are going to have different types of bonds, okay? And the stereoisomers have exactly the same number and type of bonds. Okay, so let's see a few examples of structural isomers, which will be molecules that have exactly the same number and type of atoms, but those atoms are going to be connected through different types of interactions and bonds. All right, so here we have two types or two classes of structural isomers. The first one is going to be coordination, and the second one is going to be linkage. Right, so coordination isomers. Think about the following transition metal complexes. Okay, so one is going to be this complex ion. So that is pentamine sulfate chromium 3 bromide, and the other one will be something similar but different. Okay, so it's going to be an isomer. Right, but notice that it is different, right? So they have exactly the same number of atoms and type of atoms, okay, but the bonds between them are different. Notice that these are going to be ionic compounds, and when you put this one in solution, you will get bromide ions, and then a complex ion in which chromium is bonded to 5 ammonia molecules and a sulfate molecule. When you put this compound in solution, you will get sulfate ions, and then a complex ion in which you have a direct bond between chromium and bromine atom, okay, and then 5 ammonia molecules there. Okay, so clearly these are molecules with the same number and type of atoms, but the bonds between them are different, right? Notice that again in this complex you will have a direct bond between chromium and sulfate, and no direct bond between chromium and bromine. That would be simply an electrostatic interaction. Okay, and here you have a direct bond between chromium and that bromo ligand. That would be a coordinate covalent bond, and then an electrostatic interaction with the sulfate ions. Okay, so those are coordination isomers. Linkage isomers occur when a ligand in a transition metal complex can establish a bond through two different atoms. So for example, the thiocyanate ligand can establish bonds either through the sulfur or through the nitrogen end, right? So you can think about a transition metal complex, right, where you form here a coordinate covalent bond, okay, and that thiocyanate can bind to different ways, either that way or this way. Okay, notice that those bonds are different, yet you still have the same number of atoms and types of atoms. So these two molecules would be isomers. They would be structural isomers of the linkage type. Okay, we use the name isothiocyanate to specify this type of bonding through the nitrogen atom, and simply thiocyanate to designate that the bonding is to the sulfur atom. Okay, great. So those are examples of structural isomers in which we see that the bonding is a little different. Okay, now in stereoisomers, you have the same number of atoms, the same type of atoms, and then they're going to be bonded through the same bonds. Okay, the only difference between the isomers then is how those atoms are arranged in space. Okay, and here we're going to also distinguish two types or two classes of stereoisomers. We're going to have on the one hand geometric isomers, and here we're going to have also optical isomers. All right, so geometric isomers are also called cis-trans isomers, and then require either a rigid bond or a rigid ring or a rigid plane. Okay, the way that we're going to illustrate this is with the following molecule. Okay, this is a platinum complex with which is going to be square planar. So all 5 atoms or 5 moieties of this molecule are in the same plane. Okay, but notice that this platinum 2 complex has 2 chloride ligands and 2 amine ligands. Okay, but notice that there's actually a choice about how you arrange those ligands around the platinum. Notice that you can actually have that, or you could also have a situation in which the chloride ligands are not close to each other but opposite to each other, right? So you will have this and then that, and here you will have the 2 amine ligands opposite to each other. Obviously these molecules are different. They're isomers of each other, but the bonds are the same, and the number of atoms are also the same, right? So these would be 2 geometric isomers. We call this cis, and that is trans, right? So trans is when you have that pair of ligands opposite to each other, and cis is when they are on the same side. Okay. Now, this complex is interesting because it actually has some biological activity. Cisplatin is a chemotherapy drug because it can't react with DNA double helixes, right? But the trans isomer is actually biologically inactive, right? So this is not a chemotherapy drug, but this one is. All right, so that tells you the importance of isomers in health sciences and in chemistry in general. Okay? All right, so again, these are an example of geometric isomers. In this case, we have here a cis and a trans type of complex. And then to finish this video, we're going to introduce here the concept of optical isomers. Okay, so for optical isomers, the way that these were discovered is because when you have a plane polarized light, and that is light in which the oscillating field of the photons is always in the same plane, okay, it turns out that some isomer, some optical isomer of a particular molecule will rotate that plane either to the left or to the right. Okay, so it turns out that the isomers rotate the plane of plane polarized light different ways, and that is how they were discovered. Okay. All right. So let's then try to put here an example here of optical isomers. Later on, after we discovered this rotation of the plane polarized light, we actually figured out that optical isomers are molecules that are mirror images of each other, but they are not superimposable. Okay, so here I have a couple of props to illustrate that. Okay, so let's think about these models, which are just models of, say, substituted amines, right? So here you'll have a nitrogen atom, and there you will have a lone pair, and each one of the substituents will be different, right? So this may be a hydrogen atom, this might be a methyl group, and that might be an ethyl group. Okay, and you actually have exactly the same substituents here, right? So nitrogen, your lone pair, then hydrogen, and an ethyl and a methyl, right? So the color code is the same, and you can clearly see how these two molecules are mirror images of each other, right? If you have a mirror in between those two molecules, you will see that this one is the reflection of that one in the mirror, okay? But now if you try to superimpose them, you actually find out that it's impossible to superimpose them, right? Notice that If you try to align them along this line, this atom does not correspond to that one, and this atom does not correspond to this one. Okay, so that is the definition of an optical isomer. Okay, what happens here is that optical isomers are mirror images of each other, but they are non-superimposable. Sometimes these molecules or these stereoisomers are called chiral, and chiral comes from the term hand in Latin, right? So notice that our hands are mirror images of each other, but they are non-superimposable. Okay? Right, so chiral complexes also have a lot of importance in inside our bodies, in biochemistry, because many of the enzymes that we have in our bodies are able to recognize one of these isomers, but not the other one, right? So that has quite a bit of importance as well. All right, so this video has shown you a few of the classes of isomers that are available, and we have mostly used here transition metal complexes to illustrate those types and classes of isomerism.